believe it or not, I'm still looking at non-inertial reference frames. And I really, there's two problems I want to do, but one I'm definitely going to do it, and it's right now. So I saw a couple versions of this, but I want to build my own. So the idea is to take a rotating spacecraft. And if you're inside a rotating spacecraft, you can make artificial gravity. But then what happens if you like throw a ball? So there is a version of this in the GlowScript demo programs. It's pretty good. I saw another one online that it was just a 2D graph. But I'm going to make it in WebVPython. It's going to be awesome. So let's just review what we're going to do. And then we have a lot of programming to do. I know you guys love a lot of programming. So suppose that I have a rotating space station right here. So it's a cylinder. And it has a radius r, and I throw a ball in the frame of the rotating spacecraft. In that case, I have to include two fake forces, the centrifugal force that points away from the radius, and then the Coriolis force in a direction perpendicular to the velocity. So we can calculate the centrifugal force mass times omega. Omega is the angular velocity vector across r cross omega, and then we can calculate the Coriolis force negative 2m omega cross v, and that's the velocity with respect to the frame. So I'm actually going to go backwards. I'm going to start off, and I'm going to make two spacecraft. One you're going to see from the stationary frame, so it's going to look like it's rotating, and then we're going to throw the ball. And the idea is I want to have a person in here throw the ball and then catch it on the other side. Okay. So they're going to rotate around, and they're going to get over the other side and catch it. And then we'll do it from the stationary frame, and we can see what happens. It's going to be awesome. But there's a bunch of problems here. First, how do you model the motion of these non-constant forces? So if you haven't seen this before, but yes, I'm going to break it into small time intervals. Delta t is 0.01 seconds. And then during each of those time intervals, I can calculate the net force. And then I can say that's equal to the change in momentum with respect to time. So we can update the momentum F net delta t plus the old momentum. And then I can update the position R1. That's it. And I've done that a billion times, so I don't want to go over all the details of that because I just want to do the programming. Now, so there's a bunch of ways you could do this in WebVPython. I want to make an actual spacecraft. So there's going to be some programming stuff. And I'm not the best programmer. You know that. I like to do it my own way. And this is kind of art. So let's just get into it. Let's just switch over here and let's build a spacecraft. I'm going to build the rotating one first. I'm in WebVPython. Okay, I've already picked the radius of my spacecraft, r, of 5 meters, and omega is the magnitude of the angular velocity, so 1 radian per second. Now, what I want to do is to kind of like break this into points around there. And each one of those points, I'm going to put a box. So I'm going to have like, it's not going to be completely a cylinder, it's going to be different boxes. But that way I can make them different colors and all this stuff. And there's a bunch of ways you could do this. You could do an extrusion in WebVPython, but I'm not really good at that. So you just stick with what you know. Okay, so this is what I'm going to do. I'm going to start off and just put some points around a circle, because that's the best place to start. So I'm going to say n equals 0, n equals 10. So I'm going to make 10 objects around there. Theta equals 0. So let's just make this while while n is less than n. So what I want to do is make a temporary vector that is around that circle. So I'm going to call it RT, and it's going to be capital R times vector cosine theta, sine theta, 0. And then I'm going to put a sphere there. So I'm not even going to give it a name. I'm going to say sphere position equals RT, radius equals, let's just put it R over 15. That's fine. And now I'm going to increase my value of n equals n plus 1. And then I'm going to increase my value of theta, which I don't have here. D theta is 2 times pi divided by n. So then I'll have it split around that evenly. So theta is going to be theta, spell it right, theta plus d theta. Okay, so I'm just trying to make a bunch of balls, right? Because you want to start somewhere simple. And I didn't. See, this is why you start simple. So you can't find thet. Okay, I was just so excited to build. This is kind of like the where's that? Oh, there it is. This is kind of like Python version of Lego. Okay, so there are my points. And what I want to do is replace those with boxes. So if I have, let's make a value called L, the length of the box, right? Because I want all my boxes to line up and make a circle. So let's say L is going to be equal to the circumference 2 times pi times r divided by the number of boxes that I have. Actually, did I do 10? Let's just count, because I'm kind of questioning my reality. I guess I can make this a tiny bit smaller. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Good. Okay. Because sometimes you mess things up with those counters. So instead of spheres, I'm going to make boxes. And I want to put them in a list. I'm going to need to put them in a list. So let's just make a list called walls. And it's an empty list. And so down here, instead of making a sphere, I'm going to add a box to my wall list. So walls equals walls plus, now I'm going to add a box, which is a three-dimensional object. And I'm going to make the y direction the L. Okay, so the position of this is still going to be RT. It's the same spot. And then the size vector is going to be equal to vector, let's say R over 20 L. L is the width. And then the height in the z direction, let's say that's 2. I'm just picking something. Okay, let's just see what that looks like. There. Okay, so I have all my boxes, right? But they're not in the right orientation. So now I need to go through and rotate them all. And I actually do that because I already know the angle that I need to rotate them at. Let's just rotate them. I'm going to go back through the whole thing. So for wall in walls, how about that? No, I can't because I need to d-theta it. Yeah, so let's say for I in range length of walls. Now I want to go through each item in the wall and rotate it. So walls I dot rotate. Now when we rotate an object, I need to say about what origin, and it's going to be the center of that object. So walls I dot POS. The axis of rotation is going to be in the z direction. So axis is going to be vector 0, 0, 1. And now the angle, right? How far do I rotate that one? Each one I'm going to have to rotate a little bit more. So I think this is going to be equal to angle equals I times d theta. I think that will work. Look at that. There's my sphere, my cylinder. That's my spacecraft. See? Look at that. Okay, now I'm going to do one more trick, right? Because I want to rotate it. I want to really see that it's rotating. So I want each of these panels to be different color. And we can change the number of panels and everything like that. We can do that. But let's just make them different colors. So what I'm going to do is actually I'm going through each item in the wall right here. I'm going to give them a different color. So walls I dot color equals. So color, you can give it color dot red, color dot green, color dot blue, color dot magenta, blah, blah, blah. But color is a vector, red, green, blue. So I can give it red, green, blue values. So let's just say vector cosine I times d theta, sine I times d theta, and then 1. So I'm going to keep the red, green, blue, the blue values always going to be maxed out. So 1, 1, 1, the vector 1, 1, 1 is white. The vector 0, 0, 0 is black. Okay, so you can make all your colors that way. If you didn't know that, that's pretty cool. Let's just see if this works. Okay. Yeah, we're cruising along now. Okay. Let's increase the number of points to 20. I just want to do 20. Okay, so there's a great spacecraft and it's pretty and everything. Oh, I do want to add a person. I'm going to put a person down there at the bottom. So let's add a person in there. They're going to be that person's going to be a box. So I'm just going to add it to my list. Walls equals, I don't even have to name it, walls plus a box. Its position is going to be equal to vector 0, negative, I'm going to put them at the bottom, negative r plus, let's call this person a height h. H equals 1.5. So h over 2, so that's the center of the box, and then 0. And then the size is going to be a vector. Let's say 0.2, h, 0.2. They're kind of like a cylinder. And then let's give them a color. Color equals color dot yellow. There. There's my person. So now I can have the ball on top of that person, and that'll also give me more evidence that the whole spacecraft is rotating. I'm kind of excited. This is going to be great. I'm really excited. Let's just get to it. So the next thing I want to do is to group all of these objects. There's 21 of them. I'm going to group them into one object. And so in WebVPython, that code is called called a compound. Let's make a compound object. Okay. So down here, I'm going to say, I can't remember the name. Let's call it, we already have a list of objects. So station 1 is going to be compound. And then I need to give it a list of objects, walls. That's it. And just so you can see that it works, let's print station1.pos. Let's print the location of it. It does have a position. You can tell it what the position is, but it's just going to put it wherever it wants. Now, I want to move that over to the left, right? Just so that I can have 2 of them. So let's make 2 of them. I'm going to move this. Ooh. Can't find compound. And it's O and D. But it printed it. Did it not print it? Yeah, it did it. Okay. I was moving along whether things worked or not. I wasn't going to stop for any errors, right? Okay, so let's go ahead and move it. So station1.pos equals vector -600. So that's going to give it some spacing between the 2 things. Let's just see if that works. Okay, see? Now I'm going to make station 2, and I can use another great thing. I can say station 2 is equal to station1.clone, just like the Clone Wars, and I'm going to give it a position of 600. So now I'm going to have 2 stations. Let's see if that works. I'm really cruising along here. I'm really excited. There's my 2 stations. Okay. Next, I want to make this one. This is going to be our inertial reference frame. So I want to make this one rotate. So let's make that one rotate. So now we need a time step. And then I'm going to say while t is less than, let's say, 5 seconds, rate 100. So rate 100 says don't do more than 100 calculations per second. And then I just want to rotate the thing. So if I have an angular velocity of omega, each step I want to rotate at omega dot times dt. So we can rotate station 1. Station 1 dot rotate. The origin about which you rotate is station1.pos. I don't want to rotate about the actual origin or the whole thing's going to move in a circle, which maybe is something you want. That's not what I want. And then the axis of rotation is going to be the vector 0, 0, 1, the z-axis, and then the angle is going to be omega, not angle, omega times dt. And now I need to update time, t equals t plus d, dt. Otherwise I'll be stuck in an infinite loop. I'm really having fun here. I don't know if you can tell that. There we go. Man, you just got to look at that. Okay, so now I'm ready to make my ball, and I'm going to throw my ball. Okay, so down here, let's just put it down here. Ball 1 is going to be equal to a sphere. Position is going to be equal to vector. So it's down there I want to put it at the top of that head. So that's going to be 0, it's going to be actually station1.pos plus that minus r plus h, yeah, 0. And then the radius, let's say it's 0.3 just so we can see it. Color is color.cyan. And then make trail, you know you got to make a trail, equals true. And I didn't update anything on it, so let's just see if the ball's in the right spot. Yeah, okay, good. So now let's give the ball a mass. I'm just going to give all the balls the same mass, m equals 1, because I don't really care. And then I need to give it a velocity. Okay, so let's say it has to go s equals 2 times r minus h. That's how far it has to go. And then how long does it take? I'm going to say ball1.v equals vector. Okay, so I want it to go in the y direction, so 0, and the velocity is going to be s, and the time it takes is going to be equal to omega. Let's see, so it's going to be pi radians. So it'd be times omega over 2. Right? I think I'm just going to run it. Okay, so there's my velocity. And let's just update the velocity. The velocity is constant. Let's update the position. Ball1.pos, ball1.v plus ball1.pos plus ball1.v times ct. Let's just see if that works. Here we go. I don't think it's going to make it. I'm going too fast. Why am I going too fast? Okay, let's switch to the board, because I don't know why I'm having, sometimes you gotta board it out, right? Okay, so here's my omega. So I know this, oh, I did it as s is, I got that right. Okay, so this is the distance it travels, right? S is going to be equal to, I could just do this distance times 2. So that's going to be ball.pos, minus the center of that. But I think I got that right. Yeah, I think I got that right. And then omega is going to be equal to delta theta over delta t. So delta t is going to be equal to delta theta over omega. And that's going to be equal to pi divided by 1. Okay, so I didn't have the pi in there. That was my problem. Okay, so I'm going to say the velocity is going to be s divided by pi times omega. S times omega divided by pi. So it's, okay, let's try that. So v is s not 2 divided by pi. Oh, I think it's going to make it. Look, it's going to make it because halfway, when it's halfway rotation. And then, boom, caught it. Okay, but I didn't actually catch it, and that's fine. So, pretty cool. Okay, so let's run this for that same amount of time, which is pi over omega. And then he'll stop. We're almost done, actually. Nice. Very happy. Very happy. Okay. Now let's go down to the other station, right? So I need to make another ball. So let's make that ball. I'm going to copy this. I shouldn't, but I should. I am. Ball 2. And let's just, same color, same radius, same position, except that it's going to be with respect to station 2. And then it's going to be called ball 2. So it has the same mass. Let's just give it a moment. I'm going to deal with this one in terms of momentum since I'm dealing with the force. Ball2.p. Okay, now also I need to give it the same velocity as before. So if you look, let's switch back to the overhead here. So this ball is launched up, but in the reference frame, it's going to have that same upward velocity plus the velocity in that direction. And there's more than one way to do that, but I could just say omega times r, and that will give me the velocity in that direction. So I just add those two velocities together, and that'll be my velocity in the stationary frame. They got to agree, right? Okay. So this is going to be m times vector 0. No, this x velocity is going to be omega times ball 2 dot, let's say ball 2 dot pos dot y, right? That's the r value of that ball. And then the y component is going to be the same, s times omega divided by pi, 0. So now I have the initial velocity of that ball. Okay. Now down here, I need to calculate the net force in that. I'm going to do it before, I'll do it right up here. I'll do it right here. So F is going to be equal to the centrifugal force, which is mass, times the cross product of the cross product. Oh, I need the vector omega. Let's put that right up here. Omega, I can use capital thing. It's going to be vector 0, 0, omega. Yeah. So it's going to be the cross product of omega r comma omega. Well, I have too many parentheses there. So cross that. No, I think this. So 1, 2, 3. Okay, cross that. Oh, I have 3 cross. That's why I got out of control. Cross omega r omega. There, done. Okay, now I need the Coriolis force, minus 2 times m times cross omega v. And the v is going to be ball 2 dot p. I can actually just factor that mass in, so I'm going to put that right there. There. Okay, so that's my force. Now I'm going to update the momentum. Ball 2 dot p equals ball 2 dot p plus F times et. And now I can update the position of both of them. Ball 2 dot pos, ball 2 dot pos plus ball 2 dot p times et divided by m. I think that will do it. I haven't even saved this in forever. Save it. I'm going to give you the code. You know I give you the code. That's what I do. I'm a code giver. Okay, run it. Aha. Can't find R. Yeah. Okay, let's go up here. R, let's call it R2. It's going to be ball 2.pos minus station 2.pos, right? Because the position vector is going to change with respect to the origin. I need to do that all the time. So then I'm going to, and you could call it R, but I'm going to call it R2. But I think that should work now. Let's see. Nice. Very nice. Let's just increase the angular velocity by a factor of 2, right? So then it should still get to it should get back to the person, but the person will be back at where they started. And let's just see what happens. I think it'll be fun. So let's increase this to 2 and run it. Huh. Oh, because I did, what the heck? Omega is 2. Oh, I didn't change, I did do that. Time. I wanted to go 2 twice around. And I want the velocity to be half as much. So this is just going to be this. Nope, I did it wrong. They're still in the wrong spot, right? So it had to be, but anyway, that's cool. I like it anyway. I'm going to leave it like that because it's cool. But you'll see that in both cases, the ball ends up at the other side. But why did it not end up right there? Maybe my time step's not big enough. It's too big. But I think it's working, and I think it's pretty, and I think it's artistic, and I'm pretty happy with the results. So there you go. Hope you enjoyed that. Fake forces, real forces, it's all the same thing. Okay, the end. Talk to you later.